My name is Afra Mashhadi, and I'm actually glad to be in person. I was the closest one to travel. And I'm going to present our work on privacy-aware adversarial network, which was a joint collaboration with Imperial College PhD student Yu Ting Zhan, who's graduated already, and Hamed Haddadi, who could not be here today. So before I start, and I have the advantage because I'm not online on the Zoom, I can see you guys. I want to ask you, how many of you, when was the last time, or well, let's say, how many of you, show of hands, that you shared your location with researchers for research purposes, and you were like willing to give your GPS traces over 1 year to a researcher? Show of hands if you've done that ever. Yay, one person. That's great. You might be in these data sets that I'm going to present. We'll see. But we don't know your identity, I'm sure. So that is what my talk is about. You know, a lot of machine learning community can really benefit from spatial temporal data sets. We all know that mobility of people can really help us with the data sets. We can understand more about city planning, policy planning. When things change dramatically, like the effect of COVID and people change their movements, if we know that how people move around the city, we can actually plan for better resource allocation. But this is a privacy conference, so you all know that location data is highly private. As a result, it's very rare, and the last times that any kind of a data collection in terms of larger scale location data collection was done has been before GDPR had been approved in Europe. So we all know that mobility traces are very privacy sensitive. There's been work in the past that they've shown that these are highly re-identifiable traces. Even if you stripe away all sort of like, you know, identification from them, still there's been work that they've shown even like 4 spatial temporal points were enough to identify 95% of individuals in large mobility traces data sets. So what can we do? We all know that this is a problem, and so in an ideal world, we want to have some sort of a user data that is actually real, comes from these users, let's say from a mobile network operator, and we want to be able to make this available to researchers to use it, so it should have some utility, but we want to also preserve the privacy, so we want to make sure that, you know, somebody cannot just attack and infer information about the users in that data set. So what can we do about that? Well, there are many works done in the research community in the past. Location privacy protection mechanisms are famous. We know that things started kicking off with k-anonymity, geomasking, but these approaches have been shown to be not sufficient. More recently, there's been a lot of work on differential privacy and inferential privacy, and I don't need to explain to this audience what differential privacy is, but there are also evidence that even those type of works are not enough when it comes to spatial temporal data sets. So even more recently, I would say there's more work on the machine learning-based LPPMs. So what is machine learning-based LPPM? Well, we've seen examples of that on the federated learning, where individuals don't share their traces to begin with. Some people will argue that that's also not privacy, proof. But we also have approaches such as GAN-based and machine learning-based, where they take the data from the user and regenerate synthetic traces that are good enough to be used, but they're also preserving the privacy of the individuals. Our work focuses on the third one, so GAN-based, adversarial network-based models. So what we want to create is think about it as a model that would preserve the utility. In this case, when we talk about utility, we mean next point prediction, so next location prediction accuracy of an individual that can be used for whatever the research purposes. And then 2 different privacy mechanisms. One is just basically to avoid any kind of a data reconstruction attack. So if you have an entire data set, can you reconstruct it such that it would be different enough to avoid the data reconstruction attack? And the second privacy notion is to create a better in a sense to avoid user identification attacks. So we want to decrease the number of users that can be identified in that data set, in that synthetic traces that we have generated. So here's our proposed model that relies on representation learning and adversarial network. I'm going to go through these components one by one. We have trajectory of users coming in as an input X, and then the first part of the model is in charge of that privacy discrimination, which is just going to try to reconstruct the data X to X prime such that it's different enough that somebody cannot reconstruct that data set. And that's based on the representation learning. We have a few LSTM layers and the encoding and then the decoding part which reconstruct that data. Then the encoding, the green part that you can see in this figure is fed into the utility discriminator unit. The utility discriminator unit, which at this time is limited to mobility prediction unit, just tries to say, okay, having this encoding, can I guess where is the next location of this person? Where is this person going to go next? So we want to be able to have a high utility of the data set. We want to be able to predict which this person is going to go because that's what the task is. But we want to decrease the reconstruction loss there. And lastly, we have the privacy 2, which actually is focused on a user re-identification risk. And in this case, we want to avoid re-identifying a user. So the same encoding is going through that layer with the privacy discriminator trying to re-identify that specific individual, and we want to avoid doing that. So I'm going to not go through the formulas too much. I will talk about them in the next slide. You can see the details in the paper, but here's the losses that we will calculate. So we calculate 3 different losses from these 3 optimization problem that we have at hand. One of them is a reconstruction loss, which just looks at the input and the output and calculates the reconstruction error between them. The utility one calculates the cross-categorical loss of the top accuracy guesses, and then the second privacy is actually calculating the cross-categorical accuracy of re-identifying that individual. Putting these losses together, because our problem has 3 different optimization objective or model. Now we have these 3 different losses together, so we try to have privacy, utility, and privacy 2. So we can give them, each one of them, a unit and a multiplier, which allows us then to do a trade-off between how much privacy do we want to have and how much utility we want to have. So our idea is that here we want to make sure we are maximizing lambda 1 and lambda 3, which are the privacy. And so in terms of the privacy, we want to be able to have more privacy. And then with the utility, you will see that their signs are opposite, is because we want to reduce the loss of that lambda 2. So proposing this entire box of the algorithm, what do we do next? Well, we're going to experiment on 4 different data sets. These are the well-known data sets that are available in the mobility research. And in this talk, I would mostly present the data, the results from Lausanne, given that we are in the city. But please feel free to look at the paper for more results. Then we also do training and the hyperparameter selection with the different variables that we have, such as the sequence length and so on. We also evaluate our work against 2 different baselines. So we look at LSTM TrajGAN and GIDP, which is a differential privacy mechanism. I don't go to details of these, but these are the 2 most competitive works related to ours. And we report our results based on the comparison with the baseline of optimum classifier. So how much accuracy loss and how much privacy gain we would get. Here's the results for the MDC that we have in comparison with Strajgan and the GDP-DP. Here we can see that our model with that specific lambda settings, with the model 2 with those specific lambda setting, we can see that it actually has the very little loss and huge privacy gain. With the differential privacy mechanism, we can see that the privacy gain is very large, but then the loss, the utility of the data set is completely dropped. So we can see in terms of the trade-off, our model performs the best. We also can see this better when we look at the visualization. We can actually see that in these points, which are the shapes of the hollow shapes are our proposed method, we can see that they are always higher in terms of data utility and privacy. And we can tune this, because we can tune this by putting a different lambda. We can decide whether we want to be on the top right corner, having the most amount of privacy, which it's very difficult to get on the top right corner, having both utility and privacy, or do we want to have more privacy with respect to loss of utility. But the most important thing is that thinking about this as a trade-off and having a Pareto frontier, we should not choose anything underneath that line, which means that if you choose a point underneath that line, you could have always chosen a point which had either higher utility or a higher privacy for the same data set. And I'm going to just skip this in the interest of time and encourage you to look at these results with the different lambda settings in the paper. I just wanted to say a couple of things about the future direction and what we've done. We have open sourced our work, is available. If you click on the artifact, you can use our entire code and do your own baseline comparison. I encourage you to do so. I also want to say that our next future direction is looking at the trade-off between privacy and fairness, and we've published a follow-up to this work, which is available on arXiv. So please take a look at that. And also, I wanted to thank you all and thank you, my collaborator. They're excited to hear back about what you thought about this work. So feel free to reach out to them as well, and feel free to reach out to me. Oh, can I just say one last thing? And I'm possibly looking for a postdoc if you're interested in this topic. So, and you want to come to Seattle, where it rains, like here. So, thank you.
Thank you very much. So, do we have questions for the room? Yeah.
Thank you for the talk. So I have a question about the privacy discriminator. I'm just wondering how you can design this structure of the discriminator, because I assume that the attacker's capability might be related with the structure of the modules.
Mm-hmm. So the first discriminator, or the user identifiable discriminator, like the privacy 2 part? Yeah, so that one is basically just trying to guess whether in the top, if you think about it as a probability distribution of whether it has guessed this is a correct user or not based on the traces. So it just tries to limit that probability. So if you take that softmax output and turn it into the probability of the classes, then it tries to minimize the loss of getting that answer in terms of whether that person was re-identified or not. Does that answer your question?
Thank you for the talk. I was just wondering why one of the baselines is based on geo-indistinguishability, and why didn't you go with traditional DP, since, if I understand correctly, all the data is at the server already and you just synthetically generate data. Why didn't you do it with traditional DP?
That's a very good question. Yeah, I think we chose this one, the GI DP, because this specific model was shown to be actually higher in terms of the privacy advantages on the same data set. So there was the paper that is listed here had a comparison on these data sets that showed that it outperforms the traditional DP. And I think if we had that, also just like going back to one of the slides here, we would probably see that the effect of the traditional DP would be even worse than the GIDP because it would just create a lot of noise. So in terms of privacy, it would become very good for privacy gain, but it would drop the utility of that data set. So you no longer can do any predictions on it.
I also have a question regarding the second privacy discriminator, the ones that try to predict the user. How does it scale when you add more users? Because I think it's a really sparse task to predict, and the more users, the harder. So does it occur that at one point you have so many users that it's just an impossible task to learn, and then you are not mitigating privacy because you are just not able to learn anything from?
Yeah, that is correct indeed. Actually, I think it also boils down a lot to the characteristics of the data set. So for example, we can see here some differences on that. So like if you have a data that people are very much like predictable in their, so Primov, which has been collected in Lyon and is mostly university students, we can see that it's actually very easy to predict the mobility prediction, the next point, because they all go to university and whatnot, come in the same spots. But then it's very difficult to distinguish them from each other because they all have very similar patterns. So it does boil down a lot to the data set. But the fact that we can actually tune the model to give us what trade-off we want is, regardless of the underlying data set, would still work for any scale.